Part 3 of Unit 12 is about Ka, the equilibrium constant for acids. Alright, we already know that an acid is a substance that dissociates into a hydronium ion and water. So if we were just going to write the general form, the hydrogen ion plus an anion plus water is going to dissociate into a hydronium ion and A minus. That's our conjugate base. If we were going to write the equilibrium expression for this, Ka, the equilibrium constant for this acid, is the hydronium ion concentration times the conjugate base concentration divided by the initial concentration of the acid. We leave water out because it's a pure liquid. We only put these three aqueous solutions into our equilibrium expression, and this is the acid dissociation constant for a weak acid. So here's a table of some acids and their Ka values. The acid strength increases with Ka, so the higher the value of Ka, the stronger the acid is. So we got some stronger acids here at the top, and they get weaker as we go down this chart. The higher the Ka, the more dissociation. We assume that the 7 strong acids dissociate 100%, so they dissociate so much we can't even calculate their Ka. It's so big we don't even bother calculating it. We're only going to have a Ka for weak acids. So let's look at an example problem like this. The pH of a 0.1 molar solution of formic acid at 25 degrees Celsius is 2.38. Calculate Ka for formic acid at this temperature. Our reaction that's taking place is formic acid dissociating in water, and it's going to produce hydronium ions and our conjugate base, COOH minus. Our equilibrium expression for this equation is going to have water left out of it. It's going to be Ka is equal to the hydronium concentration times the conjugate base concentration divided by the concentration of the weak acid. So this is our equilibrium expression for calculating Ka. In case you hadn't guessed how we're going to have to solve this yet, yes, we're going to have to use a Rice table. So here is our Rice table, our 2 reactants, our equilibrium arrow, and our 2 products. Let's fill in things that we already know. Our initial concentration of the formic acid is 0.1. And the initial concentration of the products is going to be 0. We're going to assume it's 0 while we're trying to calculate Ka here. Water, pure liquid, doesn't factor into our Rice table at all. We still need to write water in our dissociation reaction to have hydronium form as a product, but it's not going to factor into our Rice table much at all. Now, the other piece of information they told us was that the pH was 2.38. That means the negative log of the hydrogen ion or hydronium concentration was 2.38. So to solve for the equilibrium concentration of the hydronium ion, we're going to use something called an antilog. There's a button on your calculator that says 10 to the x. Well, we're going to do 10 to the negative 2.38. That's the antilog of that pH to find the equilibrium hydronium concentration. And 10 to the negative 2.38 power, our hydronium concentration at equilibrium is 0.004. So we're going to take that and plug it into our Rice table. At equilibrium, the hydronium concentration is 0.004. So obviously this is a change of plus 0.004. And looking at our balanced equation, everything's got a coefficient of 1. So we can put plus 0.004 here, and at equilibrium it's 0.004 for the conjugate base. So that means that the initial concentration is going to decrease by 0.004. So at equilibrium, we're left with 0.096 is our equilibrium concentration of the weak acid. So all we did there, we knew the pH, which is the negative log of the hydrogen or hydronium ion concentration. We went from pH backwards to concentration. We used the anti-log. Instead of negative log of concentration, we did 10 to the negative x, so the anti-log, to find the concentration. Now we have enough information to plug back into our equilibrium expression and solve for Ka. Ka is our products over reactants, so it's 0.004 times 0.004 divided by 0.096, so Ka is equal to 1.67 times 10 to the negative fourth. So the only new step we had there, it was a typical rice table, but we had to use pH to find the equilibrium concentration of hydronium, and then work backwards from there to fill in the rest. We can calculate the percent ionization of that weak acid. Percent ionization is calculated by taking the equilibrium concentration of the hydronium ion, dividing it by the initial concentration of the weak acid, multiplying it by 100. So, the percent ionization for the formic acid in the last question, at equilibrium our hydronium concentration was 0.004. The initial concentration of the weak acid was 0.1. That times 100 is equal to 4% ionization. So, it's obviously a very weak acid. If a strong acid dissociates 100%, this one only dissociated 4%. So this is our, just remember that this is our general form for calculating the percent ionization of a weak acid. Let's look at another one. This time we're going to calculate pH from the Ka. So we need to find the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius, and Ka for acetic acid at 25 Celsius is 1.8 times 10 to the negative fifth. So our equilibrium expression for this one, Ka, is going to be the products, which is the hydronium ion, times the conjugate base, it's the acetate ion, divided by the reactants. We're leaving off pure water from our dissociation reaction, it's just the HC2H3O2. So this is what we're going to use. We know what Ka is. We're going to have to try and find the hydronium concentration to take the negative log of it to find the pH. I left water out of this rice table so I'd have more room to actually fit numbers in here. So this dissociated into hydronium and the acetate ion. Let's think about what we know. Everything's got a coefficient of 1, so this is going to be a change of plus x, so at equilibrium it's x. Not plus x, it's just x down here. Now our acetic acid is going to change by minus x, so at equilibrium it would be 0.3 minus x. I'm going to tell you about something that's going to make our lives a lot easier when we're solving these weak acid problems. It's called the weak acid assumption. Ka for this reaction was 1.8 times 10 to the negative fifth. If we kept 0.3 minus x here and we ended up solving for what x is so small that our answer for the equilibrium concentration of the acetic acid would round back to 0.3 anyway. It's such a small change that it doesn't really affect this concentration. We'd end up rounding back to 0.3. So we can write, to show that we're using this weak acid assumption, that 0.3 is so much greater than x that x is going to be equal to 0.3, or approximately equal. That's what my kind of wavy equal sign means. We can only use the weak acid assumption when Ka has an exponent that's to the negative third or lower, so negative third or more negative than that. If it's relatively high Ka, like it's an exponent of only 10 to the negative second, we can't use the weak acid assumption because there would be enough of a change that it would affect our equilibrium concentration. But since Ka is so small, that means X is going to be so small that it's not really going to affect the equilibrium concentration of the acetic acid. So we can take this minus X out of there and just leave it at 0.3. Now, whenever you use the weak acid assumption, you have to write this down to show the AP grader that you're using the weak acid assumption. If you just arbitrarily take out minus X, it might take points off of you. So you're showing the AP grader that 0.3 is so much greater than X that, I don't know why I accidentally wrote X down here, that our equilibrium is going to be approximately equal to 0.3. Hopefully that didn't confuse too many of you. We're assuming that X is so small that 0.3 minus X is going to round back up to 0.3 anyway for our equilibrium, not X. The equilibrium is going to be approximately equal to 0.3, not X. X is a very small number. Sorry about that. So now that we've used our weak acid assumption, we know that Ka is going to be equal to x times x, so x squared divided by 0.3. This is a lot easier to solve than having 0.3 minus x on the denominator of our equilibrium expression. What it means is we don't have to use the quadratic formula now that we've used that weak acid assumption. So as we start to simplify this, we'll end up with 5.4 times 10 to the negative 6th is equal to x squared. We take the square root of that, we get x is equal to 2.3 times 10 to the negative third. Now we're not done. This is not our final answer because they wanted us to find the pH. So we have to take this term, plug it back into our Rice table, and take the negative log of it. pH is the negative log of 2.3 times 10 to the negative third, so our pH is actually going to be 2.64. This is the answer we were looking for in this big question. So the new stuff we added here was the weak acid assumption. Whenever Ka is 10 to the negative third or more negative than that, we can assume that X is so small that the equilibrium concentration of the weak acid will round back to its initial concentration, so we can ignore it in our Rice table. We just have to remember to show that the concentration is so much greater than X that the equilibrium concentration would be approximately equal to its initial. Again, remember, you have to show the grader that you're using the weak acid assumption. So what we've done so far is just worked with monoprotic acids. Monoprotic means one proton, one hydrogen ion. There are also polyprotic acids. They have more than one proton. If the difference between the Ka for the first dissociation, the removal of that first hydrogen ion, and the subsequent Kas is 10 to the third or more, the pH generally depends only on the first dissociation. So for most of these, the pH of these different polyprotic acids only depends on this first Ka. Most problems that we deal with are only going to be looking at the first dissociation, the removal of the first hydrogen ion. Your question for this section: HF has a Ka of 7.2 times 10 to the negative fourth. Use a Rice table to determine the pH of a 0.75 molar HF solution. Remember to use the weak acid assumption.